Okay, you can go ahead and shut the door. So today I am going to discuss a little more about supersymmetry breaking in the, or not a little more, I am going to discuss for the first time supersymmetry breaking in the MSSM. And I'll start by reminding you of some rule that I derived last time, which is that the super trace of n square is minus 2. Remember how I wrote it last time. G raised dA summed over all u1 factors in the gate. Okay. So this was the sum rule. Now we want to see whether with this sum rule we are in a position to implement spontaneous supersymmetry breaking. Can you just close the door, please? In a position to implement spontaneous supersymmetry breaking in the MSSM. This was all in a very theoretical framework, just in various abstract models, and now we want to do it in MSSM. Just to remind you, the super trace over m square means the mass square of the scalars minus, roughly speaking, 4 contributions from mass squared of fermions and then plus 3 contributions from mass squared of vectors. So that's why I defined it last time. Okay. So, how does this work? Now there seem to be 2 answers to this question in the literature. I emphasize that it's difficult for me to have an opinion on these things just like that because I'm still a beginner in this subject. But I can tell you what are the 2 answers and I'll try to discuss one of them now and one of them next time. They are in any case not mutually contradictory. They lead to the same physical conclusion, but there are somehow 2 different ways to think of it. One is that even with such terms as I've written above, one gets phenomenologically unacceptable constraint on particle masses. And I'm going to explain that now. The other point of view is that considerations of anomaly cancellation make such terms unacceptable anyway. In the context of the standard model. So this I'll discuss next time. It won't hurt us to take the first point of view because even if we assume that such D terms are there and supersymmetry is spontaneously broken and this mass sum rule holds, we'll be able to see that within the standard model, because of the very precise nature of the gate group and the charge assignments, we'll be able to show that that the constraint on particle masses is incompatible with phenomenology. Okay, so for that we need to think of this MSSM, and let's work with the MSSM below the Higgs scale. That means below the scale of the Higgs waves, which are assumed to break the electroweak symmetry down to U1 from S2 cross U1. Now, in today's lecture and also for a few more lectures, I'll keep talking about the theory below the Higgs scale, though I've never actually told you the precise Higgs potential which leads to Higgs waves. And the reason we can do that is The only thing that the Higgs potential does for us is to give the waves. But that's another problem, if you like, and it will also lead to some phenomenology associated with Higgs particles, which we won't focus on now. But as far as the waves themselves, we already said what we think the waves will be. There are two doublet Higgs. One will have a wave V1, the other will have a wave V2, and they'll be in the place where the neutral component of that Higgs is. Okay, I hope you remember all that. Because the doublet Higgs have one charged and one neutral component for each one, and the other is one neutral and one charged. So it's the two neutral components which can have waves. Those waves are V1 and V2. The ratio of V2 over V1 is tan beta. If we assume all that, we don't have to go into the detail of how all that happens, but we can extract the consequences from that. So we are assuming that. Now one consequence is that there can actually be two D terms. It's a little surprising, and in fact it has been confusing me for the whole weekend, but I talked to Sandeep a bit and I think this is sorted out. You would think that there should be only one above the Higgs scale because SU2 cross U1 has only one U1 factor. Okay. Technically, when I take a trace like this, all the SU2 generators are traceless, only the U1 generator has a trace. Okay. Below the Higgs scale, there is only one U1 generator because SU2 cross U1 is broken to just U1, and that U1 is called Q, and it's equal to I3 plus Y by 2. This is the diagonal generator of SU2, and this is the hypercharge. Okay. Now the reason there can be two D terms is that hypercharge, we agree there can be a D term because it's a generator with a trace. For the other one, because the Higgs has a wave, we can actually make a gauge invariant object analogous to this on the right hand side using the Higgs wave. Okay, so below the Higgs scale there really are two D terms, and so we'll proceed just using that formula, assuming that there is D3 can have a wave and dy can have a wave, where D3 is the D term coming from SU2, the 3 component, A equals 1, 2, 3, and dy. Okay. If you want, we can go into this assumption in more detail later, but for now let's make this assumption, which I notice is made by Briscoe, Bolle without any explanation at all. And if we make this, then our formula for the super trace becomes minus twice G2 I3 D3 plus Gy Y by 2 dy. Just that formula expanded over these two possible D terms. Okay. Now, in order to calculate this for any particular supermultiplet, what are we calculating? This is the splitting in mass squares within one supermultiplet, which should be 0 if there is no supersymmetry breaking, and it will be non-zero if there is supersymmetry breaking. So we can do this multiplet by multiplet for all the fermion multiplets of the standard model. For example, the up quark superfield, the down quark superfield, the electron superfield, and the neutrino superfield. These are the 4 A's.
So this assumption here is that the D terms corresponding to both this I3 group and the Y group both have constant, but there would be some alternative.
No, the surprising one is that this is there at all.
That okay. You can assign them also.
Yeah, because this formula, if you read it literally, will give you dy and will give you y by 2 from this and dy, and that's the end of the story. Okay, but actually there's a contribution from the diagonal part of SU3, even though technically that generator is traceless. Because that TA is sigma 3, that is traceless. However, you can make a gauge. The point is whether you can make gauge invariant combinations, and that you can do using Higgs fields. Okay, but I'm not writing it down in detail here. You can think about it, and we could discuss it next time. Okay, so now in order to get this contribution for each fermion multiplet, we simply need to remind ourselves of something we did right in the beginning, in the first or second lecture of this course, which is to write down all the hypercharge and SU2 assignments for the various leptons and quarks, except that now it will be extended to lepton supermultiplets and quark supermultiplets. Obviously, they have to have the same quantum numbers because the MSSM must include the physical particles with all their right properties. So So to remind you, within one generation we had the electron multiplier L1 containing L nu E and Le, and we had E bar, which was also chiral multiplier representing the positron and its superpartner, and we had Q1 equals Q up and Q down, and then we had U bar and D bar, which were SU2 singlet chiral multipliers representing the anti up and down quarks. Okay, so this was the entire first generation of quarks and leptons in MSSM, and whatever I do will obviously apply to each generation separately. In fact, even within this generation, it applies to each of these superfields separately. This one, and these. Okay. For all of them, for each of them separately, there is a super trace of M squared. But I'll group them in the following way. First of all, let me write down the quantum numbers. So let's do it like this. Just you need, I guess we all need to be reminded. I certainly need to be reminded from time to time. So here's I3, and here's Y, and here's the superfield. Okay. So this one has half and minus 1. This is in the same multiplier of SU2, so it must also have half. Sorry, this has minus half, it's a lower component. It must have the same hypercharge. Okay. E bar 1 has 0 and plus 2. Remember when we did the standard model, instead of discussing the left-handed positron, we discussed the right-handed electron. For the right-handed electron, this is 0 and minus 2. Okay. But now because of supersymmetry, we prefer to discuss everything in terms of left-handed or chiral superfields. So whatever was right-handed, we conjugate and then supersymmetrize. Okay, so these are chiral, not anti-chiral superfields, and they have the opposite quantum numbers from the right-handed counterparts because complex conjugation is involved. So here we have half and minus half, 0 and 0. We can read this off because this is part of an SU2 doublet and these are the singlets. And as far as the hypercharge, it has to be the same for these two, but it can be different for the next two, and it's minus 4/3 and plus 2/3. So that's just reminding you of the various quantities we need. Then we just have to calculate out this formula. Oops. That was a mistake. Write it on the top. So let's do an example. Let's do me square, mass of the electron, and what we'll do is we'll take this guy and also this guy, the left-handed electron and left-handed positron, and add all the contributions. Here, we could even do it separately, but we just define these quantities because remember we are looking for a conflict with phenomenology. So we can define any quantity we like and calculate it, and then argue that that value contradicts something in experiment. So for me squared, we get G2 C3. This comes from taking this guy, putting Le equals minus half, putting I3 equals minus half in this term, so we get this, okay, and putting Y equals minus 1 over there, I get plus dy dy, okay, and then adding the contribution from this one, this has y equals plus 2 over there, so I get minus 2 gy dy. Is it clear how the calculation proceeds? Okay, so the final answer is G2 D3 minus gy dy, and now it's very easy once you've seen one example. You can do all the others yourself. I'll just write down the answers. Here you get minus G2 D3 plus Gy dy. This is for the neutrino. Here there is only a contribution from this, and there is no right-handed neutrino by assumption for the moment. So that's the full answer. As far as the quark, the up quark supertrace is the same thing as this. And the down quark supertrace is this. And you notice a very interesting pattern. All of them are proportional. Okay, so it need not have been so. For example, if we just work with a left-handed electron multiplet, we would have got just these two terms. This came from the left-handed positron. Okay, so it's the way we have defined things. Here also, this contribution is from the left-handed up quark as well as the left-handed and up anti-quark. Okay, so once you do it that way, then you see that all of them are proportional to the same thing with a value plus of some quantity, minus of same quantity, minus of same quantity, and plus of the same quantity. And therefore, from here, you easily get that supertrace of the electron masses plus that of the neutrino masses is 0, and also that the supertrace of the up quark masses plus supertrace of down quark masses squared is 0. Okay. So suddenly, in spite of assuming that there was the most general d-term breaking possible, which does split the individual multiplets, we find that when we take the supertrace not over a single supermultiplet but over more than one, for example here over all the quarks in one generation, left and right, up and down, then we still get a sum rule saying 0 on the right side. The same thing if we do it over the leptons. Okay? So these are some rules which are true even after d-term supersymmetry breaking. But they are due to the fact that the most general allowed supersymmetry breaking, which is this in this MSSM, can be calculated because the quantum numbers I3 and Y of every field are already fixed by phenomenology. That's not up to us. We can't play with that. We could add some, there are ways out of this, but within the MSSM, this is a precise sum rule. And now, this is the problem because it means that some quark, squark or lepton has to be light. This means in every generation, notice that this is a sum rule generation by generation. So in every generation, some squark or lepton is lighter than its right? Because unless that was so, there's no way that these variations within the mass squared spectrum could all add up to 0. This is like summing up over the bosonic minus the fermionic mass squares. But as far as these chiral multiplets are concerned, that's only the scalars and fermions. The scalars are all squarks and leptons. The fermions are all physical quarks and leptons. Okay. And if the total masses of one are equal to the total masses of the other, then it must be that it cannot be that all the squarks and leptons are very heavy. Some, in fact, must be lighter to restore the balance. Okay. So this contradicts experiment. We are not yet, or I am not yet at the precise level of familiarity to tell you where it contradicts experiment. What I understand is that maybe in the third generation you could get by, because remember the quark and leptons in the third generation, up and down, top and bottom and tau and nu tau are all very heavy. So maybe we could get by if there's something sitting approximately at that mass scale, which is a squark or lepton and a lepton, and we may not have found it. But this requires that there's a for example, a quark or lepton that's lighter than the up or down quark or the electron neutrino, and that seems like something very light that we in the GeV range, the single GeV range that we should have found. Okay. Now this could be solved. This could be overcome. You understand, this is a very serious difficulty because it says that spontaneous supersymmetry breaking is out in the MSSM. Okay. This is the point at which, in some sense, people could have gone home and said MSSM doesn't make any sense, there's nothing we can do with it. The reason they persevered is that MSSM itself is motivated by a desire to achieve some high-scale unification, and then people realized that, well, it's perfectly acceptable to have some kind of explicit SUSY breaking at this scale, which is induced by some high-scale effects. Okay. But before you go to that assumption, you realize this could be overcome by adding extra U1 factors in the gauge group. If we had extra U1 factors, then we could have a new Phi-Diopoulos T term for that U1 factor, and we could make it anything we like. But then we would have to go through a lot of contortions to make sure that the resulting theory doesn't contradict experiment in all sort of other ways. Okay. For example, that extra U1 must have associated to it a gauge boson which would be called this. If you call this U1 prime, there will be a Z prime. You have to make sure the Z prime is heavy enough. You have to worry about anomaly cancellation. So this introduces lots of other problems. And that doesn't mean it can't be done or it shouldn't be done. But I think it's fair to say that therefore this is not minimal. So it's not part of the MSSM. At no stage in this course have I said that MSSM, the minimal supersymmetric standard model, is necessarily the one we are looking for. The real model might be something not minimal, with lots of extra features and lots of extra ways of evading contradiction with the experiment. But it's not minimal, so at our level of understanding, we'll postpone this kind of direction until we have sort of conquered the minimal model, and then we can think about more complicated things. Given that, so the only possibility within the MSSM is to introduce soft, explicit SUSY breaking terms. I checked with Sridhar, and this is the correct way of writing SUSY breaking, so we've been on our list. And we assume that these are generated by some high scale. But the correct way to say it is, we assume these are generated within some other sector which is called the hidden sector, whose fields are neutral under the standard model gauge. So we assume that there's another unstated or not stated in detail sector of the theory. It has some fields, some particles. Those don't carry any charges under SU3 cross SU2 cross U1. That in particular means they don't carry electric charge, they don't carry weak charge, they don't carry strong charge. So they are largely undetectable in a direct way. But they communicate with the MSSM through some heavy messenger fields. Okay, and it's very tempting. Of course, these are very old ideas, probably 15-20 years old, but it's very tempting for a string theorist to make a cartoon of this situation, saying that I emphasize I don't want it to be taken as anything more than a cartoon for now, but these are the MSSM brains. And these are some hidden sector brains. And then here are some states that are charged under both. Okay, it's very natural in a brain picture to imagine that you have some fields which are charged only under this part of the group, which correspond to strings going within these brains. Another set of fields that are charged only under this part of the gauge group, and a third set which are charged under both gauge groups. Okay, so it's just a picture, but of course eventually it gets taken more seriously than that. But this suggests, for example, if this is some separation in an extra dimension, then the minimum length required for such strings would set a mass scale for the messenger fields, and then the theory would have spontaneous supersymmetry breaking in the hidden sector, and it would be communicated as an explicit supersymmetry breaking to the visible sector. So this is called visible sector. So more than anything, it's just an idea or a way of thinking about the problem, and we'll see as we go along how much sense this makes. But our first duty is that if we are assuming this, we promptly forget about these and those and just focus on the possible effects on this side, on the visible sector, because that's the MSSM. Okay. Good. So that brings us logically back to the MSSM Lagrangian after several lectures, and we realize that LMSSM must be replaced by LMSSM plus L soft, which are the soft SUSY breaking terms that we are allowed to add. And then this, after completion by adding a Higgs sector, will be the complete Lagrangian of the MSSM. The physical one, the one in which supersymmetry and the SU2 cross U1 electroweak symmetry are both broken, and then we can actually compare that model with the experiment in principle. Okay. Now let's recall that L soft I wrote down last time in a model or theoretical context what were all the possible terms that we could deal with in L soft. Okay. And now what we have to do is take those and put into those the actual standard model fields. So for example, last time, so I'll do it like this, which I hope will help you get a flavor of what's going on. Last time we had written such a term. Take the bosonic field from any chiral multiplet, which could be a Higgs multiplet or a fermion multiplet, and just give it a bare mass term of the phi star phi, right? So this was one class of terms in L soft that we discussed last time. Now the question is, what possible terms in the MSSM does this one term give rise to? And here's the answer with all independent coefficients. So here are the quark, or rather squark fields. The index I is generation 1 to 3. Left, if you remember, means left-handed squark is the super partner of the left-handed quark. It's not handled by itself because it's a scalar. Okay. Then we'll give this left quark its own mass square ij in flavor space. Okay, L is a label, it's not an index, and I and J are flavor indices, and tilde means the super partner. So if Q was a quark, then Q tilde is a squark. So here's one term. But these are only the left-handed guys. We need corresponding terms for the right-handed guys. Also remember that the left-handed guys are SU2 doublets. So this Q contains both up and down left-handed. Okay, and there's a contraction between these, which is possible after all because this is an SU2 doublet and this is its complex conjugate. Please notice here one very amusing thing. This kind of contraction was not possible in the fermions because you couldn't contract undotted with a dotted fermion. Okay, that's why if you remember fermion mass terms were always QL, QL plus Q dagger L, Q dagger L. They were never Q dagger L, QL. That's why the Higgs mechanism is what gives the mass to fermions. But with the scalar partners we have no such problem because there is no handedness. So you can always take an SU2 doublet and multiply it or dot it invariantly with its complex conjugate doublet. That's perfectly right. So with squarks you can have a bare mass term and this is it. As far as the right-handed squarks, which means the squarks which are superpartners of the right-handed quarks. Now here we have a little bit of notational inconsistency, but I think we can manage. Let me write it first and tell you what my problem is with this. So this is BGR notation. The problem I have, of course, is that the right-handed quarks and squarks are not in a chiral superfield, they are in an anti-chiral superfield. Okay. So I would have preferred to call this one, instead of calling it the right-handed squark, I would have liked to call it the left-handed anti-squark. Or but I think I could have, and then rename this correspondingly the other way. But it probably won't matter if we do it this way. If you're not appreciating this point, maybe it's not even worth worrying about. So we need certainly one independent one for the D and the U type quarks because being singlets, SU2 singlets, they are not related by anything unlike this term. Okay. That takes care of all the possible squark masses of this form. The next thing we have to put are the electron masses, but it's very similar. For the left-handed electrons, we put in the doublet L, which contains the neutrino and the electron, analogous to this. So this is the neutrino and this electron, and then this. Okay. And then for the right-handed or for the singlet electrons, we'll put a term for the electron and we won't put any bare mass for the neutrino on the grounds that we are postponing all discussion of neutrino masses till some very late stage in this course. So there we are. So that takes care of the electron masses in the soft SUSY breaking piece of the Lagrangian. And what does that leave? What else can we add? We've done the quarks, we've done the leptons, and we've done all the three generations, so that's all over. What else can we add like this? And remember I said that these files are the scalar fields in a chiral multiplex, so are there any chiral multiplex not accounted for? Come on guys, huh? No, neutrinos we agreed that we are not going to put mass terms for those because we're just going to treat. We're going to forget about. Yeah, but the thing is, the neutrinos, the left-handed neutrinos are included here, and the right-handed ones won't exist since the right-handed neutrinos don't exist for this purpose. Okay. Well, Higgs, thank you. There's still Higgs. Okay. Now, what can we write for Higgs? So. Yeah, there will be a minus sign over everything, by the way. Okay, that's this minus sign. Okay, so for the Higgs, we can have one term involving the scalar part, which is the actual Higgs, H1, Again, remember it's an SU2 doublet, so it has to be dotted with itself. Okay. And then another term involving H2 star and H2 with an independent mass. Okay. Things don't come in generations, so there's no mixing. Okay. Also, they don't have similar quantum numbers. H1 and H2, if you remember, have quite different quantum numbers. And if we wanted a cross term between H1 and H2, then you realize that it can't be of the form H star H, because H1 has a negative and a neutral charged object, and H2 has a neutral and a positively charged object. So a cross term between H1 and H2 has to be H1 H2 and not H1 H2 star, which means it can come and is going to come, but it's not under this category. So here's category 1. There are 3 more categories that we need to think about. First, we'll dispose of one that's relatively simple. Remember that in LSoft there were terms like Ci, Phi I. Do you remember? There was Ci, Phi I, then there was bilinear terms Bij, Phi I, Phi J, and then trilinear terms Aij, K, Phi I, Phi J, Phi K. We'll come to each of those in turn. But the point being that all of them were supposed to be holomorphic or analytic in these complex fields plus their complex conjugate, not times their complex conjugate. So they are not of this kind of form at all. Okay. Now these, of course, have a very poor chance of being there at all, because every term is supposed to be gauge invariant. And can you think of any scalar in the standard model that's gauge invariant all by itself? It would have to be neutral under everything. There's no such scalar. End of that. So that's the end of this term. That also teaches us that that Ci Phi I term can only be there if we have gauge invariant or neutral, gauge neutral particles that are neutral under all gauge interactions. Which in practice means they interact only gravitationally or through some other gauge interactions that are not part of the visible sector. Okay. Good. So actually category 2, since we ruled out something, category 2 will start with Bij, Phi I, Phi J. Okay. So what are we allowed in this category? This is also interesting because we still have to make something gauge invariant, but we have to make it gauge invariant using only phi's and no phi stars. And the phi can be either the quarks or the leptons or the Higgs. These are all the scalars we are allowed. And we are looking for a bilinear term among quarks or leptons or Higgs, squarks or leptons or Higgs, which is gauge invariant. And by the way, we did talk briefly about R symmetry at some point, and so everybody here has an R symmetry assignment, and we shouldn't break that either. Okay, so under R symmetry, the squarks and leptons are all odd. Because this is absolutely fine. This is anyway fine under any phase symmetry you can think of. And that will tell us that even if we found a term which seemed to mix a squark with the Higgs, that would be ruled out by R symmetry, but I don't think there are any such terms in any case. So, in fact, the only term I can think of, and apparently the only term there is the one I just referred to a few seconds ago, a dot product between the first Higgs and the second Higgs. Okay. What are these guys? These are the scalar part of the first Higgs doublet chiral superfield and the second Higgs doublet chiral superfield. And this dot product, because they transform the first and second Higgs doublets, although they are both holomorphic, they transform oppositely under SU2. That's how they are defined. And therefore there is an invariant dot product between them. Now we can put an independent parameter in front of this because it's part of soft SUSY breaking. But we should realize that such a term was already there in the MSSM. Okay. Now, where did that term come from?
R symmetric preserving.
Yes, R symmetric preserving what interaction? Yeah, mu H1 H2, where H is a capital H. That is, in the superpotential, there was a mu capital H1, capital H2. All the sorry.
No, H1 dot H2.
H1 dot H2. However, we should realize that with that term, we don't get small h1 dot h2. We actually get small h1 star h1 and small h2 star h2. I hope that point is clear. So in that sense, we don't actually have such a term already. But in the superpotential of the MSSM, we have capital H1, H2, and its coefficient is mu. So by convention, people choose to call this coefficient mu times the mu number p. That is, just parameterize the coefficient of this as p mu H1, H2. Okay, so p is the parameter for this. It's a free parameter. All the parameters in the soft Lagrangian are free. So this. Okay?
What about these structures have superpotential?
No, I don't believe that.
If it's allowed here, it must be allowed.
Yeah, in the superpotential you have a term mu H1 dot H2. Right? So what is your question?
When you come up with the cubic ones, there'll be something that's allowed in the not something that's allowed in the superpotential.
That's right. That's correct. So these terms all are somehow modeled on the superpotential, but they are actually and we'll see why that's a useful way to think of them a little bit later. But they're actually just bosonic terms. And the important thing to realize is that though they formally look like terms in the superpotential, they are not, in the sense that if you take the superpotential expressed in superfields and then write it in ordinary fields, you'll never get something that's holomorphic plus complex conjugate in the boson sector. You always get W, I mod squared. So it's rather strange, but as we'll see in a moment, we already saw that probably. Once you introduce the Spurion field, then this becomes more natural.
For this comes.
Yeah.
This comes from. This will come from something like d eta mu h1 dot h2 in the super formalism.
Actually, that H1.
No, this can't come from any term in the superfield formalism. This
No,
is
this is Spurion.
With the Spurion.
So
With the Spurion, it will be B eta H1 H2. It will be a cubic coupling involving. That is, I think, correct. Wait, let's just check that's correct.
Because H1, H2
Yeah.
are the scalars.
Yeah.
So eta will take out the scalar.
That is absolutely correct. So it will come from the Yukawa coupling, if you like. Well, not Yukawa coupling. It will come from a coupling between the F term of the Spurion, which is just 1, and the scalars of this. That's correct. Okay. So this term is there. The next thing to look at are the cubic terms, which are, in the general case, I wrote it AI, JK, Phi, I, Phi, J, Phi, K, and this translates into, now these are somewhat non-trivial, so I'll write them out in a little bit in detail. So let me write it. I think all the notation should be clear. So let's do a quick check to see if the notation is clear. First of all, these are all scalar fields. And what are they? This is the Higgs, the scalar of the first Higgs doublet. Is the first Higgs doublet, the scalar part. This is the slepton, left-handed, and this is the star of the right-handed selectron. Okay, so let's see how the charges work out. The electric charges are such that sorry. Yeah, Higgs, no, it's a doublet, and in fact, this doublet is dotted with the left-handed slepton doublet. Okay, so that makes it neutral both. Ways, because if you remember, the slepton doublet, nu E and E has electric charge 0 and -1, and this Higgs hopefully has charge +1 and 0. That's correct, now. And then they are dotted using that epsilon symbol, which matches this one with the -1 and the 0 with the 0. So this combination is electrically as well as SU2 neutral, but now we seem to be in deep trouble. I've done something wrong. This simply cannot. No.
It is SU2 neutral, not electrical.
It's not electrically neutral, but in that case, See, something is still wrong because this guy has a possible electric charge of 1 or 0, right? This also has correct. Thank you. It's the other way around. What actually happens is that the neutral one from here comes with the -1 charge from here. So let's look at the electric charge. Yeah, sorry, I just said something wrong. So there are two possibilities. This can give me either 0 or -1. Okay, because H1 I think has 0 and -1. Can you just check from your notes, somebody? I never remember this thing. H1 has 0 and -1, H2 has 0 and +1. Hopefully. This is always +1.
H1 has 0.
-1, very good. And this has -1 and 0, so the invariant combination between them will pick out either the neutral Higgs with the electron and the positron, selectron and the positron, or it will pick out a negatively charged Higgs, neutrino and the positron. Okay, so both of them will be electrically neutral, and of course this dotting is SU2 neutral, so we've taken care of everything. Last question is, what is this stuff in the middle? Well, because of the structure of this, which is again R symmetry is responsible, we have two sleptrons and a Higgs. Okay, the Higgs is even, the sleptrons are each odd under R symmetry. Okay, so out of all the possible AIJKs, two of these indices are fixed to be sleptron indices and one is fixed to be the Higgs. So effectively AIJK turns into just a second rank instead of third rank tensor. One of them is just fixed to be Higgs. Okay? So it's a matrix IJ. Now what is that matrix? We can give it any name we like, but we already have a matrix Fe, which was the mass matrix for the electrons and the selectrons in the MSSM, in the supersymmetric part. So instead of parameterizing this by a new name, we put in a new matrix AE, which multiplies Fe and the whole thing appears in this term. It's the same philosophy as calling this coefficient B mu. Is that point clear? It was called mu in the analogous term in the superpotential. So here it's called B mu. And here this analogous term in the superpotential was called Fe. So here it's called FEA. So AE is the new parameter. So that's one term, but that's by no means everything. There are a few more terms like that. And they are all governed by being SU2 and U1 neutral. That's all. You can try to write down anything you can think of. So here's the next term. It's H1 dot. Now the same story with quarks. That's bound to work. Then this coupling will be called FTAD IJ. And here we'll have either a down or an up squawk. Okay. And again, you can check that the charge assignments work in the same way. The SU2 is between these two, and the electric charge or the hypercharge you can just add between all these three and find that it's 0. So this one involves the Higgs with the quark doublet and the down squawk, and there's an analogous term with the up squawk, but in the case of the up squawk, the other Higgs shows up. And the SU2 invariant combination is written like this. These are the parameters, and here is the up. Okay. And everything here being complex has got plus complex now. So is this clear? This is all the allowed by R parity terms of the form phi I, phi j, phi k. Okay. They could in principle have been, so there can't be couplings, there can't be cubic couplings only between leptons and squarks, because then it would be R odd. There also can't be couplings with one lepton or squark and two Higgs, that would also be R odd. In principle, there could have been a coupling between three Higgs, but three Higgs, although it's R even, there's no SU2 invariant combination you can make because there are no Higgs singlets in this model. All the Higgses are doublets, so you can't make a singlet out of three doublets. Okay, but there are non-minimal extensions with singlet Higgs, and then you could have those terms. So you should always keep in mind that terms that we are not writing, and we are not writing for some definite reason. In some sense, we are writing the most general terms we can think of writing. Okay. Now, I didn't really want to rub this out, but I've run out of space and I still have one more type of term to write. But maybe we'll fit it in up here. So category 4 of terms, does anybody remember what those were in the MSL, in the general soft SUSY breaking Lagrange? Gauge-Eno mass, thank you very much. Excellent. So the Gauge-Eno mass in the general model was a half m lambda a plus complex conjugate. So this is my strategy in each term. I've written the generic term and then I've written it out for you in the MSSM context. Generic term, MSSM context, generic term, MSSM context. Here's the generic term. Now it's up to us to put in suitable parameters for all the Gauge-Enos in the theory. And here I have an issue with Rees-Gottwald-Leroy. They may have had their historical reasons for their notation. I find it simplest to always say that a super partner is got the same, has the same label as the original field, but with a tilde on top. Okay. So since these lambdas are either the super partner of the B gauge field, which is called the BNO, or they are super partners of 3 W bosons, so those are VNOs, or they are super partners of 8 gluons, and they are gluinos. And so I'll write them at least in a notation that I can easily recall. M1 for the hypercharge Gauge-Eno. So B tilde is the name, and it's just a 2-component fermion undotted plus Cc. Then there's the VNO, and finally these are W8. So the gauge field W would be W upper A lower mu. Instead of mu, I've suppressed the spinor index and put a tilde. That should keep you reminded that it's the super partner of W. Likewise for B. And the third one, of course, then is M3 and the gluinos. And again, you're supposed to realize on your own without help from the notation that this A goes from 1 to 3, but this A goes from 1 to 8. One big fallacy in many textbooks is that if you introduce enough notation to keep everything distinct from everything else, then the first student will actually remember by page 350 what all that notation was. It's a huge nightmare. So I hope that I've slightly made the notation a bit rational. You should be able to read off from any term what the particles are and whether they are fermions or bosons, whether they have hidden indices and everything. Well, I won't say I invented most of it. Most of it is the same as in the books, but a few things are changing. Okay. Yes.
Masses to Higgs.
Yeah. So the point is that the Higgs, there are already Higgsino masses because there's already a superpotential for the Higgs in the supersymmetric part. Now, by giving masses for only the Higgs and not for the Higgsino, we are splitting the masses between Higgs and Higgsino. In other words, if you want to change the Higgs mass, if you want to change the Higgsino mass, you can add something here and add something in the MSSM sector, and between them the net effect would be to change the Higgsino mass. But I may come back to this point because I have not completely understood the issues about why you choose to write what you write in the soft SUSY breaking part of the action. So, but we will return to it. Okay. Good.
So these M1 square and down there,
yeah.
Last line, M1 square and M2 square are not the Higgs masses.
No. These are additional mass terms. In fact, this and this and this and the Higgs mass coming from the MSSM. When you diagonalize the entire thing, you get the physical Higgs masses. Okay. And we'll see something simpler, which is that the fermions also mix, and we'll have to diagonalize fermion masses between the Gauge-Enos and Higgs-Enos, and that's what we are going to do next. Okay. So, in fact, that's going to occupy the entire rest of this lecture. So here it is. The only thing, this is the entire soft SUSY breaking Lagrangian, and these are the parameters which we try to constrain by theoretical inputs as well as by experimental inputs. And the important thing to realize is that this is the stuff which is responsible for the huge proliferation of parameters in the supersymmetric standard model as compared with the ordinary standard model. You must have heard something about 19 parameters in the standard model between Yukawa couplings and CKM phases and so on, and coupling constants. But here what's happened is there's all that, and on top of it there is, let's see, so starting here, here's a matrix mixing between generations, 3 by 3 matrix. Okay, this is real because each of these terms is real, there is no complex conjugate to be added. So it's a real 3 by 3 matrix, but probably not symmetric. And there's another, and there's another, and another, and another. So that's 5 3 by 3 matrices. So that's on the order of 45 parameters right there. Okay. Of course, you can perform some rotations on these fields to diagonalize out or remove part of the matrices. But remember that the same fields appear in the MSSM. So you can only perform rotations here which don't mess up what you've done over there. In other words, in MSSM, if you try to diagonalize that part of the fermion mass matrix, of the scalar mass matrix, then you won't be able to undo that here. So these will all be, or you'll have to freshly diagonalize the whole thing. So it's a lot of parameters. Okay. Then there are two more here. Luckily, the x's don't mix in these terms. So these are just two masses, two real masses. Then there's one B here which is complex. Okay. Then again there's an AE, AD and AU which are all complex 3 by 3 matrices. Okay. And then there's an M1, M2, M3 which are all complex numbers. Okay. They have to be just numbers because of course all 8 gluinos have to have the same mass term. Otherwise it would break SU3 and so on. Well, if you add it all up, very rough count gives 100. Supposedly the exact count gives 105. That's pretty close. So the 105, there are roughly 105 parameters here in front of you. Maybe one or two of these 105 were already written earlier, like the mu term we introduced earlier, mu capital H1 dot H2 was already introduced earlier. That's also a parameter of MSSM that's not in the standard model. But the point I'm making is most of the parameters are not in the supersymmetric part of the MSSM, but in the soft SUSY breaking terms. And that's hardly surprising because the supersymmetric part is the standard model, judged up by only one thing, which is the extra Higgs doublet, and then supersymmetrized. But the whole point of supersymmetrization is that per se it doesn't introduce any more parameters, because you just take the existing Lagrangian and then you make everything a superfield with the same coupling. So there are no new parameters except because of that extra Higgs. Okay, so there's tan beta because of two different Higgs waves, and there's mu. These are the two new parameters in the MSSM, and then there are hopefully 103 on this black model. So that should make 105. But I may be wrong by 1 or 2. Anyway, this fact is often the source of great depression, because after trying to solve a hierarchy kind of problem and introducing supersymmetry, we are rewarded by having a much less predictive theory. But you see, I'm not the expert to talk about this, but my point is, there are two different goals. The standard model is supposed to explain physics as we know it. The MSSM is not needed to explain physics as we know it. In fact, the standard model is great for all physics that we know. It's supposed to lead us in the direction of a unified theory. Okay, so if this had been a nice complete theory by itself with very few parameters, we'd have been a little mystified, because where is then the need for unification? Okay, somehow it's introduced in order that there be a high energy unified theory. So that means that all these 105 plus the original 25 parameters or 20 parameters should all be predicted by some dynamics in the underlying high energy theory. That's the philosophy, take it or leave it, but that's what it is. Okay. So now we turn to something which is influenced by but not solely dependent on the terms I've written here, which is mixing between A-genos and Higgs-genos, which is a rather important phenomenon of the MSSM. So before that, are there any questions on what I've done up to now? Yeah.
Is the Higgs potential that causes electric breaking in ESM?
It's not in here anywhere. So the philosophy we've been taking, I just briefly mentioned it in the beginning, is that we assume the two Higgs doublets have waves 0, V1 and V2, 0. and we don't ask where they come from now, but we will in another. And actually, it's because I'm following this portfolio and Roy chapter by chapter, but I have not always followed the logic of their presentation. But in this case, I eventually became convinced that this makes sense, because everything we deduce, and we'll be deducing a lot just now, is premised on the fact that these H1s and H2s take given waves, and the Higgs sector is first of all set up to give those waves, which we don't think would be a very hard job, and secondly set up to give the phenomenology of Higgs or Higgs and these particle more than anything the Higgs-Higgs interactions, because the interactions between Higgs and these particles are already on the bottom. Okay, so only when we need to worry about Higgs self interactions or Higgs gauge interactions, those are not on the board. Actually, even Higgs gauge interactions are on the board. Sorry, that was a wrong statement. Because again, those are contained in the covariant derivative. So the only thing that's missing is the Higgs potential. So it's a separate subject that we can postpone. Okay.
Repeating myself, but this M1, M2 will also get, I mean, the masses of Dinos and Dinos will also get the same terms from the Higgs symmetry.
The masses of Pinos and Vinos will get contributions from that. That's
so the M1 and M2 are not the masses, right? Again, you have to add them on.
Yeah. Oh, sorry. That's exactly what I'm going to do now. They will get contributions from that, and in fact, that's what induces the mixing. I'm about to show you that. Okay. So the question that we are asking now is, what are the masses of Pinos, Vinos, Uinos, and Higgs-Inos? First of all, why are we focusing on this? So let's tell you. The fermions in the MSSM that we know are the leptons and quarks. Okay, so let's put those aside for the moment. The MSSM has introduced a whole bunch of new fermions. What are these new fermions? They are the ones which are the super partners of either scalar or vector fields, which we already want, and those are the Higgs and gauge fields respectively. So their super partners are the Higgs-Inos and gauge-Inos. So Dries Roy book describes these as non-matter fermions. It's a slightly tortuous terminology, but it does contrast them with the matter fermions, which are leptons and quarks. Okay, so these are all non-matter fermions, and all of them have odd R parity. Okay, good, and all of them mix because these generically mix with each other because of the terms I've written here as well as the terms that were written in the MSSM. And so it's a fresh mixing problem we need to solve besides the generation mixing problem for quarks and leptons. Namely, what are the mass eigenstates for gauge-Inos and Higgs-Inos? In general, they are neither of them, but they are linear combinations. So as soon as I discuss it, this will become clearer. I want to stress though that some of the terms responsible, that this phenomenon doesn't come from soft-SUSY breaking. It's already there in the MSSM, but it's influenced by terms in the soft-SUSY Lagrangian also. So you can't discuss it until you have written down L-soft, which we have just done. Okay. Now the key term, if you like, responsible. So before we go into the details of it, we make a couple of observations. The key term responsible is the term of the type G2, W, tilde, H, tilde, H. So W tilde is a Vino, so it's a fermion. H tilde is a Higgs-Ino, so it's also a fermion. So the fermion indices are contracted between these, and H is a Higgs field. Now, if you believe that such a term is there in the theory, then you see that it's mixing gauge-Inos and Higgs-Inos. So we better diagonalize it along with H tilde and W tilde terms, which must be there elsewhere, and which in particular are clearly visible here. Here's a W tilde term, okay, and H tilde comes from the original Higgs superpotential. Yes.
So this W tilde is sitting in the adjoint representation.
Yes. Is the adjoint representation of the SU2.
And H tilde H, okay.
Yeah, and H tilde H, so this is, thank you. So he's trying to figure out how this becomes a singlet. This being a Higgs is a doublet. This being a Higgs-Ino is also a doublet. with two SU2 doublets and a triplet, you can make a singlet. Okay, so the first thing and I haven't put any indices because now we are going to do it. I'm just showing you schematically. I haven't told you whether this is H1 or H2 or what, but this is schematic. But let's ask where it comes from. It comes from a term. So the Higgs, remember, is a charged chiral superfield. So there will be an H dagger e to the 2 G2 B H. Okay, this is the D term, kinetic term, gauge invariant kinetic term in the MSSM Lagrangian, and it's pretty clear that this in particular implies terms like that, because from one of the H's I'll pick out the scalar part, from the other I'll pick out the fermion part, so I've got one theta, and then from V I pick out the cubic in theta term which has a gauge eno. Okay, so that's 3 more thetas, along with that makes 4 thetas, they get eaten up by the integration. So is this point clear? This is where it comes from, generically. And this also answers your question, because this is a doublet, this is a doublet, this is a triplet for SU2, and this is exactly how the gauge invariant Lagrangian looks.
So what are these H1 or H2?
Yeah, so that I'm not saying here, but in this, okay, in this it's H1 and H1 or H2 and H2.
Both are the
So in fact they'll be the same. I hope. Let's see as we go along if that's correct. R symmetry doesn't act independently on H1 and H2, but the kinetic terms are always, for any chiral superfield, they are phi dagger of that one times itself. Okay, so this is one comment. The second comment is, of course, gluinos don't mix. That's clear. Gluinos have SU3 quantum numbers, but Higgsinos don't. Higgsinos are doublets of SU2, come in doublets of SU2, as well as they have hypercharge, but they don't have any, they are completely SU3 neutral. So gluinos don't come into this story. So the only things that are going to mix are the Vinos and Vinos with Higgsinos. Now that's 2 comments before we actually get started. Okay. The third comment one can make, perhaps I should make it here, is that mixing will only take place among Higgsinos and or Higgsinos of the same electric charge. Since this mixing is a phenomenon generated by Higgs wave, and since giving the Higgs a wave breaks the symmetry from SU2 cross U1 down to U1 electromagnetic, therefore it's sensible to think of the physical states afterwards as eigenstates of electric charge. But now we'll have some gauginos that will be plus or minus charged and some will be neutral, because remember the gauginos came about as partners of the W's and the Bino, or W and Z in another basis, and we know that W3 and Z are neutral, W plus and minus are charged. Okay. Likewise with the Higgs, we know that 2 of the 4 components of the Higgs are neutral and 2 are charged plus and minus. So all the charges match actually very nicely. Okay. There are plus and minus Higgsinos and plus and minus gauginos, and there are neutral Higgsinos and neutral gauginos. So we can discuss the mixing of the charged guys separately and the mixing of the neutral guys separately. So let's do that. Once you get all these things straight, it's extremely simple. Okay. So first we are going to discuss the charginos. So chargino will be the name given to the mass eigenstates obtained by mixing charged gauginos and charged Higgsinos. Those are called charginos, and these are going to be in principle detectable physical particles. Okay, and the other set which will come to next will be the ones obtained by diagonalizing neutral gauginos and neutral Higgsinos, and they will be called neutralinos. Okay. So the mixing part, or if you like, the part responsible for the mass, probably the best name to give it is charge mass. As we expect, it's going to be a mixed thing involving charged kGnos, charged xenos, and bilinear terms with one of each of this type. Okay. The only restriction now is that I will only focus on the charged guys. So I claim the answer is the following. Now here I've also inserted into this answer the wave of the Higgs. So in this box, let's remind ourselves that H1, here 1 and 2 are the two different Higgs doublets. Okay. In DGR's book, there's an upper index which tells me whether it's the up or down component, but I find that extremely confusing. I prefer to label them by the electric charge. So anyway, the wave of H1 is V10. We've done this before. This is just to remind you. And the reason is that in H1, this field is neutral and this one is negatively charged, while in H2, this one is positively charged and this is neutral. Only the neutral ones can have a wave. So these are the two waves. Okay. So now I'm going to write out the mass terms, assuming that the Higgs in this kind of term is replaced by one of these two waves.
So the term, the one should be starred.
One of the H's should be starred, yeah, very likely. Very likely. Yeah. Okay, and in fact here it is. Let's see if this lives up to your expectations. This is V1. Okay, so once it doesn't matter that it's starred because the waves are taken to be real. So it's V1 W plus xeno 1 minus plus V2 wave of the second Higgs W minus xeno 2 plus. So here we see at least something that fulfills our expectation, which is that the Higgs and the xeno are of the same family. So this is H1, then this is the wave of H1. The wave of H1 comes with H1 tilde, and the wave of H2 comes with H2 tilde.
It should be W tilde.
W tilde. Very good. Exactly. Okay. So these I claim are all the terms involving charged Higgs and charged kGnos that come from this sort of thing. Okay. But of course then there are direct mass terms, and one of them came from soft SUSY breaking Lagrangian, and that's the we know mass term. If you remember, we put this in. We had put it in the form W tilde A, W tilde A, but if you take the 1 plus and minus I times 2 component with the square root of 2, that gets rid of the half here as well as right puts this in, plus its complex conjugate. So this came from L soft. And finally, mu H1 tilde minus H2 tilde plus CC. This came from the superfield coupling mu capital H1 dot H2. Okay. So out of all of these, the only term from L soft is this middle one. The first and last come from the MSS, the supersymmetric part of the MSS. Okay. But you can see, of course, that L soft is going to be very important because, of course, this term will play a crucial role in diagonalizing this whole business. So, but once we have this, then it's very easy to write the mass matrix and diagonalize it. So, let's do that somewhat explicitly. So I claim this can be written as W tilde minus H1 tilde minus, and the matrix M2 G2 by root 2 B2 G2 by root 2 B1 and mu plus C. Now you notice that this matrix is not anywhere near being Hermitian or anything. In fact, all its entries are complex, or most of its entries. M2 is complex, mu is complex. These are real, but then they are not equal to each other. So it's not Hermitian in any sense. Okay. But if we call this matrix X, then the simplest way to solve the diagonalization problem is to consider the Hermitian matrix X dagger X and diagonalize that and take the square root. Okay. Why is that the thing to be done? Well, because with this structure where this basis and this basis are different, notice that these are totally different. There is H1 here and H2 here. Okay. That means that actually you will diagonalize this by making one unitary transformation on this and a different one on that, which we referred to earlier in this course as bi-unitary transformations, this delicious mathematical idea. So bi-unitary transformations will diagonalize X, but that means that unitary transformations will diagonalize X dagger X. Okay.
So the
Now,
two unitary matrices are basically one is diagonalized to X dagger X and another diagonalized to X.
excellent, that's absolutely correct. In fact, here it is. So as per these people, we have X goes to U star, this is their choice of conventions, B inverse, U and V are both unitary, and this will lead to a diagonal answer M1 tilde and M2 tilde, which will be the Chargino mass eigenstates. Okay, but under this, it's pretty clear that X dagger X goes to V, X dagger X, V dagger, and X dagger. So this is diagonal, and this goes to U what? U star X dagger U transpose. So first is also diagonal. Okay, these two relations follow from that one. So we can simplify our lives by computing X dagger X, which will be a Hermitian matrix by construction, and then diagonalizing it, finding the eigenvalues, and then it's clear that the square roots of those eigenvalues are M1 and M2. In any case, it's more satisfying to find the square. Well, it's as good to find the square. Okay, so let's write this matrix. X dagger X is not a hard computation, considering this is X. One new input that one new notation that people like to use here, which makes physical sense, is to recall the relation between these parameters V1, V2 and physical particle masses in the MSSM. So use, I think I've written these before, mass of the W is a half G2 square root of V1 square plus V2 square. Okay. Tan beta is V2 by V1, and therefore from this you can get cos and sin beta, and finally you have that G2 V1 which appears in that mass matrix is twice MW cos beta, and G2 V2 is twice MW sin beta. So before we calculate X dagger X, we first replace G2 V1 and G2 V2 over here by these masses and beta, so that everything is parameterized by mass terms M2, mu, MW, and then beta, the angle, which is a very key parameter of MSS. So from here you can easily deduce that X dagger X dagger X is Right. So as promised, this is the Hermitian matrix, and also as promised, it depends on MW, which comes from the Higgs waves. It's the geometric mean roughly of V1 and V2, so the square root of V1 square plus V2 square up to a factor. Beta, which is the ratio V2 over V1, and then M2, which is a soft mass parameter for the we know, and mu, which is the original MSSM parameter, mu governing the coupling between two Higgs fields H1 and H2. It depends on all of these. So it's hardly rocket science to find the eigenvalues of this matrix, and the eigenvalues are m tilde 1 and m tilde 2 given as the roots of a quadratic equation, m squared plus m2 squared plus twice mw squared plus or minus some long sort of thing. Not awfully illuminating.
It should be m tilde 1 square in it.
M tilde 1 square. Thank you so much. That's correct. Okay?
What is that? 4mw square cos square 2 beta.
Yeah, cos square 2 beta. This isn't awfully exciting, but in a few minutes we'll see some characteristics of this in certain limits, maybe even now. Okay. In fact, let's see it right now, because I should finish. So, by convention, chi tilde 1 plus and chi tilde 1 minus, which have one mass m1, are defined such that this mass is less than the mass of the other eigenstate. Okay, and so there are basically 4 charge zeros made out of 2 gauge zeros and 2 Higgs zeros. And the interesting thing is, let's look at some limits. So the interesting limit here, one of the possible limits is that mu, the parameter mu, is very large compared with these are the gauge. Okay, so M1 didn't enter in this because M1 is the Beano mass term. We haven't done neutralinos, we've only done charginos. But let's keep it here. And this is much greater than MW and MZ, which also didn't enter here. Supposing we take this limit, then you see from here that the off-diagonal terms are pretty much negligible because MW is the smallest thing. We can also forget about MW from here, and so we have already a nearly diagonal guy with M2 and mu, but we've taken the limit where mu is large, M2 is smaller. So that means that the lightest charginos are gauginos, and the next heavier are Higgs. These are all approximate statements in this limit. Is that clear? In the reverse limit, if mu is much less than m1, so let's reverse the order of the soft SUSY mass, breaking mass m12, and make it much larger than mu, but again make it much larger than MW and MZ. Okay. Again, in such a limit, the off-diagonal terms can be neglected, but now it says that the lightest guys are the guys of mass mu, but mu is the mass of Higgs-Inos. So the lightest charge-Inos are Higgs-Inos. So there we have it. That's all I need to say for the time being about charge-Inos. We have a matrix, we diagonalize it, we get some masses. It's a complicated formula, but we can use it. And in these limits, we see that in these two limits, the mixing approximately disappears, and bulk of the contribution to the light charge is gauge type, and here it's Higgs type. And we'll see that when we do neutral Inos, which I'll do next time, it will be exactly the same. The lighter ones are gauge type, or the lighter ones are Higgs type in these two different regimes. That's actually a one-line calculation, but I'm out of time, so I won't do that now. Okay.